Hello and welcome to the first video of the semester, covering section 1.5 on limits. The study of calculus is driven by the concept of limits, so that is where we'll begin. Let's begin with the function sin x over x. You'll recall from your pre-calculus review that the domain of f is all real values except 0, as division by 0 is not defined. This means that f of 0 does not exist. There is a hole in the graph at x equals 0. There may be no point for x equals 0, but we can ask the question, what value is f of x approaching when the x value approaches 0? This question is the concept of a limit, and limit is represented mathematically by the symbol lim. Looking at the graph, it seems as if sin x over x really wants to be defined at x equals 0. This feeling is caused by the position of points surrounding 0. There is a trend towards 1. If we zoom in, at this magnification, it is clearer that the immediate neighbors of x equals 0 are trending towards 1. Let's zoom in again. All the points in this magnification are very near y equals 1. And if we continue to zoom in, the points on our screen would be closer still to the value y equals 1. However, there will continue to be a hole at x equals 0, as f of 0 is not defined. That is, f of 0 doesn't exist, but as x gets closer to 0, f values get closer to 1. A concept written mathematically, which is read, the limit of f as x approaches 0 is equal to 1. Let's investigate the rational function f. The domain of this function is all reals except 1, as division by 0 is not defined. F of 1 doesn't exist, but what is the limit of f as x approaches 1? In our graph, the values about x equals 1 are trending towards y equals 1. Let's zoom in. We still see the same trend in this magnification. And in this magnification, almost all values are near y equals 1. If we continue to zoom in, it becomes clear that the limit of f as x approaches 1 is 1. When describing the graph of a function, there are two topics which can describe the graph, an actual value and a limit. The limit of f as x approaches a being L means that you can make the values of f arbitrarily close to L by choosing x values sufficiently close to a. A way to visualize a limit is to imagine ants crawling along a function towards a fixed x value. As we are dealing with functions, there is only one point on the graph per x value. So when we say that an ant is crawling towards the x value a, we mean that the ant is crawling along the points on the graph, and the x values of these points are approaching a. There are only two directions that an ant can crawl towards a point from. The positive side, the right side, that is the points on the curve where the x value is greater than a. And the negative side, the left side, that is the points on the curve where the x value is less than a. For a lack of better names, Lefty the ant crawls from the left side, and Righto the ant crawls from the right side towards the value x equals a. If the ants meet when they approach the x value a, then we say that the limit exists. If the ants fail to meet, then the limit does not exist. In this graph, both Lefty and Righto will meet at the x value a, therefore the limit exists. But in this graph, Lefty and Righto will not meet at x equals a, so the limit does not exist. The y value that the ant Righto is approaching while crawling towards the x value a is called the right-handed limit, while the y value that the ant Lefty approaches while crawling towards the x value a is called the left-handed limit. A right-handed limit is denoted by a positive behind the a, and the left-handed limit is denoted by a negative. So when we talk about the ants Lefty and Righto meeting, we mean that the left and right-handed limits are equal. In this picture, the left and the right-handed limits are not equal, so the limit does not exist. A limit exists only if the left and the right-handed limit are equal. Let's discuss the limits of the function f as x approaches a, b, and c. When Lefty and Righto crawl towards the x value a, they meet at the same value s. This means that the limit exists and is s. However, the actual value of the function x equals a is r. Remember, the limit and the actual value are separate. When Lefty and Righto crawl towards the x value b, they do not meet. In fact, they would have to jump, not crawl, in order to meet. The limit does not exist as x approaches b. Also, notice that the actual value at x equals b is completely independent from the left and the right-handed limits. When lefty and righto crawl towards the x value c, they are challenged with a climb. If an ant would have to crawl upwards indefinitely or downwards indefinitely, as is the case here, then we say that the limit is infinite. Here, the left-handed limit is negative infinity, while the right-handed limit is positive infinity. Be careful. When limits are described using infinity, they do not actually exist. They just fail to exist in an interesting way. The term infinity is not a number to be used in calculations. It is a term to describe unbounded size. There are three scenarios in which a limit can exist and be equal to a value L. In all three, both lefty and righto, the left and right-handed limits, equal L. In the first scenario, the actual value f of a exists and is L. In the second scenario, the actual value f of a exists but is not L. And in the third scenario, the actual value f of a does not exist. It is important to note that the limit and the actual value are separate things and do not depend upon each other. About 2 minutes ago, we encountered an example with ants crawling in infinite directions, and we saw that left and right-handed limits could be positive or negative infinity, a value symbolizing unboundedness that we don't use for calculations. One last piece of terminology. The line x equals a is a vertical asymptote for f if the left or right-hand limit as x approaches a is infinite. So in both examples, y equals 1 over x and y equals 1 over x squared, we have a vertical asymptote at x equals 0. Okay, at this point, given the graph of a function, you should be able to visually identify left and right-handed limits, identify two-sided limits, and identify infinite limits and vertical asymptotes. You have the basics, now it's your turn to strengthen that knowledge by practicing on your own.